Last week in Shanghai, Huawei announced that they have done two things at once. They have broken out of one of the most fundamental constraints in the history of electronics, Moore's Law. And they have broken out of a restriction that was specifically designed by Washington to stop them from ever building advanced chips at all. Since 2019, the Dutch company ASML, the only company on the planet capable of producing the machines used to manufacture the world's smallest transistors, has been blocked under US pressure from selling that equipment to Huawei. The strategic logic was simple. No machines, no advanced chips. The gap widens every year until it becomes impossible for them to close. This week was Huawei's answer to that calculation, and they are calling it logic folding. Hi, I'm Sirat, a lawyer turned cybersecurity specialist. With a background in law, tech, I analyze how technology, cybersecurity, and geopolitics collide to shape a global power. And this decision banning chips to China is exactly where all three of those forces meet at once. So the question is this claim real? What does it actually mean in practice? And is this a clever architectural workaround or something far more fundamental? To answer that properly, you first need to understand something about Moore's Law. The first transistors were roughly the size of your thumbnail. One of the earliest programmable computers, the ENIAC, filled an entire room, weighed 30 tons, and could perform around 5,000 operations per second. Compare that to the chip inside a modern smartphone, around 20 billion transistors, each just 3 nanometers long. That is 2,300 times smaller than a single red blood cell. And they execute trillions of operations per second. That compression happened because of one thing, done over and over for roughly 60 years, making the transistors smaller. Each reduction in size gave you more transistors per unit area. More transistors meant more computing power. More power at smaller scale meant lower cost per operation. And that progress compounded in every direction simultaneously on a reliable schedule. This is what Moore's Law actually describes. It is not a physical law, it is a commercial observation about what the industry had managed to deliver and an implicit promise that it would keep delivering it. For around 6 decades, it helped engineers build entire roadmaps, investment cycles, and product generations around the expectation that transistors would keep shrinking and performance would keep following. But that era taught us an unhealthy obsession with transistor size. And what if transistor size just is not the right metric anymore? What do you think about the Moore's Law and its barriers? Write them in the comments below after hitting the like and subscribe buttons. A transistor is essentially a switch. It is built from two semiconducting regions with a gate bridge between them. Apply a voltage to the gate and it opens a channel for electrons to flow through. Remove the voltage and the channel closes. When you make a transistor smaller, the obvious benefit is fitting more of them into the same area. More transistors, more compute. But shrinking also means the channel gets shorter. So the transit time for electrons drops and the smaller gate has lower capacitance, meaning it charges and discharges faster. So the transistor itself becomes a faster switch. So far, so good. But here's where it gets complicated. The wires connecting these transistors also get narrower, and narrower wires have higher resistance. Halving the width of a wire roughly quadruples its resistance. Multiply resistance by capacitance and you get the RC product, a direct measure of how fast a signal can actually travel through a circuit. Even when the transistors itself is getting smaller and faster, the wiring connecting them can make the entire circuit slower. There's also a hard physical wall coming. Keep shrinking the transistor channel and it becomes so thin that electrons start to quantum tunnel straight through it, bypassing the gate entirely. The transistor becomes unreliable. This is the fundamental physical limit that classical transistor scaling is heading toward, and the entire industry knows this road has an endpoint. Here is what makes this interesting. For advanced nodes below around 10 nanometers, the RC delay of the global wiring can be 10 times larger than the intrinsic switching delay of the transistors themselves. This is why clock speeds have largely plateaued at around 3 to 4 GHz and broadly stayed there, even as transistor counts have kept doubling. Once you accept that transistor size is not the be-all and end-all, the signal propagation time might be the more important metric. You start to look at the chip design very differently. Instead of optimizing in space, you optimize in time. And suddenly, design approaches that seemed fixed start to look more flexible. This is the core insight behind Huawei's logic folding. Instead of laying a circuit out flat, transistors, wiring, logic gates all arranged across a single horizontal plane and connecting distant logic gates with long horizontal wires, you stack layers of active circuitry directly on the top of one another. Gates that used to be far apart in a 2D plane are now immediately above or below each other, connecting through extremely fine vertical bonds. The critical path, the shortest path a signal needs to travel to complete a specific computation, which previously might have run along the full length of the chip, can now run vertically through it. Think of it like this. Imagine moving from a single-story factory where all your machinery is laid out flat across 2 dimensions to a multi-story building where you stack processes vertically and give critical components a much shorter distance to the other component they depend on. The work gets done faster not because the machines get better, but because the layout got smarter. The critical engineering challenge here is something called the bonding pitch, how closely placed the vertical connectors between layers can actually be. For logic folding to deliver its full potential, Huawei determined that the bonding pitch needs to be less than 3 times the top middle pitch. In practical terms, that means signals do not need to travel far horizontally before they can find a vertical connection to a different layer. The current industry standard for this distance is around 10 micrometers. Most in the industry assumed that was close to the limit. Huawei claims they have achieved down to 2 micrometers with essentially 100% yield in manufacturing. Now I want to be clear about something. 3D stacking is not a new concept. I have worked with chiplet companies before. You take separately manufactured chips and bond them together physically on top of each other. This is exactly what happens in high bandwidth memory, a wedge of memory placed on top of a GPU to give your graphics card access to extremely high memory bandwidth in small footprint. But this is not what logic folding is. With conventional 3D stacking, each chip is designed for 2D first. Optimized for a flat plane, the 3D element comes at the packaging stage. The chip design itself is never built around the vertical dimensions. Logic folding enters the design process far earlier. During the layout phase, you identify the signal paths with the tightest timing constraints, the connections actually throttling the chip's overall speed. Then you fold those paths so they sit closer together vertically. The architecture itself is built around the 3rd dimension from the ground up. So what do you think? Do you think the logic folding works? Drop your thoughts in the comments below. I read everyone and share my own thoughts as well. Let me walk to you what Huawei have actually published, keeping in mind that independent third-party validation has not yet been done. The current chip, the generation before any logic folding implementation, sits around 155 million transistors per square millimeter. Getting from the previous generation's 126 million to that 155 million figure took the team a full 3 years. That is a 23% gain over 3 years. But that's also exactly what you would expect. Geometric scaling with older lithography approaches is hitting a ceiling. Now compare that to their next chip, the Kirin 2026, scheduled to ship this autumn, this fall, is quoting 238 million transistors per square millimeter. That is a 53% density gain in a single chip generation. That number is directly comparable to the pace of Moore's law at its peak. For context, TSMC's N2 process, currently one of the most advanced nodes in production anywhere on the planet, planet sits at around 292 million transistors per square millimeter. So Huawei remains behind the leading edge, but they have closed the gap significantly using a fabrication node that was understood to have entirely plateaued. Huawei's roadmap claims that by 2031, by expanding logic folding across more chip components, transistor density could reach the equivalent of 1.4 nanometer architectures. To be precise about language here, they are not claiming they can physically fabricate chips at 1.5 nanometers. The equivalence is about transistor density achieved through 3D implementation. That places them around 3 years behind where TSMC expects to be through conventional geometric scaling alone. 3 years behind the global leader, without accessing to ASML's machines. That is the number worth sitting with. Beyond density, there are downstream performance metrics that matter even more. Because they can route signals vertically through the chip, the current 2026 requires 50% fewer clock buffers. The components that boost the timing signal as it travels across the chip. That means half the area, half the power, just to keep the chip's internal heartbeat running. Clock skew, the timing gap that opens because the signal arrives at different parts of the chip at slightly different moments, is down 25% this way. Skew forces engineers to run chips slower than they theoretically could to let that lagging signals catch up together. Reducing it means the chip can run closer to its actual performance ceiling. The average data path, the circuitry that actually executes computations, has been reduced by 60%. The same logic in a 60% smaller footprint than previously required. These factors combine to produce the headline number. The current 2026 CPU performance core is running at 3.1 GHz. That number is significant because sustaining a performance core reliable above 3 GHz requires the kind of interconnected precision that until now advanced lithography was considered the only route to delivering. Most of the industry had written that milestone off as unreachable for Huawei without access to ASML's equipment. And the 2031 target, a 5 GHz processor in a mobile class chip at reasonable power consumption. To put that in context, Apple's latest silicon and Qualcomm's Snapdragon peak their performance cores between 3.7 and 4.3 GHz. Desktop chips from Intel and AMD can hit 5 to 6 GHz, but with power and thermal requirements that have no place in a phone or a compact AI server. Sustained 5 GHz in a mobile chip at a reasonable power, that number is not being hit by anyone today. If TSMC is on nanometer class silicon in 2031 and Huawei is delivering 5 GHz on a stacked architecture without advanced lithography, that means the performance conversation between those two chips is broadly the same. That is the ambition of this roadmap. Now, there are things worth saying here that the press release are not leading with. I think they are actually the most important parts of this announcement for anyone genuinely trying to assess whether this is real or not. First, the design tools largely do not exist yet to support logic folding at scale. The EDA software, the CAD tools that chip designers use to lay out circuits, were built entirely for 2D geometry. Logic folding requires a fundamentally different set of design methodologies and tooling. Huawei has built preliminary versions of what they need. Part of this announcement and part of what they have been so loud with it appears to be a deliberate signal to the broader industry to invest in developing these tools collaboratively. What this means in practice is that even if the underlying design principle is sound and delivers significant value, there is only a certain speed at which the broader industry can adapt and roll it out. The tooling gap is of course real. The second major challenge, and probably the harder one, is thermal management. The more layers you stack together, which I'm sure you wanted to talk about this in the comments too, the more difficult it becomes to extract heat out of the chip. Chip thermal design power has been increasing every single generation, and concentrating circuitry vertically makes that problem significantly worse. Huawei's own president of chip design flagged this explicitly as a major challenge on their roadmap. How they solve it between now and 2031 is probably the single thing I will be watching most closely to see how they will deal with this. So, do you think this actually changes the chip war? Drop your thoughts in the comments below, and if this kind of analysis is useful to you, hit the like button and subscribe now. The conventional framing of this story, and it is the one that most coverage has defaulted to, is geopolitical. Huawei was locked out of the advanced fabrication tools. They found a way around the fence, semiconductor Cold War drama. Classic. And yes, all of that is real, but I think it misses something important. We already knew Moore's law was running out of road. The advanced lithography machines that the export controls are designed to protect access to are not scalable either. ASML's current EUV tools are approaching the resolving limit of 13.5 nanometer wavelength light. The next generation high-NA EUV extends that roadmap, but not indefinitely. At some point, you genuinely cannot make transistors smaller. Silicon atoms are discrete particles. You cannot have a transistor smaller than an atom. What I think Huawei has demonstrated, or at least credibly claimed to have demonstrated, is that there is a parallel path to the same destinations, complementary to conventional scaling and available when the conventional route hits the dead end. A path that arrived early from an unexpected direction, developed by a team that simply had no other choices. Whether Huawei's specific implementation performs as well as claimed, we will know when the current 2026 ships this fall and independent benchmarks are run. But the physics of the approach is sound, and that part of the story does not depend on trusting any particular company's press release. TSMC, Intel, Samsung, they are all developing advanced 3D packaging. They are doing it from a position of abundance as a next step. Huawei did it from a position of scarcity as the only step. It's worth asking whether the end of destination of both approaches might ultimately look similar. The easy angle the most journalists have taken it is that this is a sanctions evasion story. I would push back on that. There is more interesting questions here. The one I will be watching over the next few years is whether this architectural approach opens up post-geometric scaling paths for the entire industry, and whether the whole industry ends up walking them. If it holds up to scrutiny, this is not just China's answer to America's export controls. It might be the industry's next chapter, arrived early from an unexpected direction by a team that had no other option, and that is worth understanding properly regardless of which side you are rooting for. As a lawyer turned cybersecurity specialist, what strikes me most about this story is not the geopolitics, though that matters. It is the reminder that constraints, real constraints, sometimes produce the kind of thinking that abundance never would. Washington wanted to close a door. It may have opened a different one entirely. The current 2026 ships this autumn. The benchmarks will tell us whether the claims hold. I will do the benchmarks myself too. By that time, I will be covering it as well when they do and when I do. Until then, do you think this actually changes the chip war? Drop your comments in the comments below. I read every single one and respond. And if this kind of analysis is useful to you, hit subscribe because the next video is going to be even more interesting.